This is the first video of Unit 2, Matter. We'll look at parts A, B, and C. This unit is divided into 3 videos. This one includes parts A, B, and C, as we mentioned. The second video includes parts D, E, and F, and the last video, part G, organic compounds. A little background first. Substance is a general, non-specific name for matter. Matter includes elements and compounds. Elements are pure forms of matter. Compounds are made of combinations of different elements. Matter is composed of particles. Elements are made of atoms. Compounds are made of molecules. A third kind of particles are ions. All particles are in constant motion. They move fastest in a gas, slower in a liquid, slowest in a solid. Mixtures include solutions. Particles are dissolved and the solution is clear. Colloids. Particles are dissolved, but the solution is cloudy. Suspensions. The particles do not dissolve, but they settle to the bottom. Solutions are mixtures of solute and water. Water is a solvent. Now, in chemistry, we refer to solutes and solvents. In biology, we refer to solute and water. A fluid is a solution, so you hear phrases like body fluid. Now let's look at the chemical elements. Chemical elements are composed of atoms. The human body contains roughly 26 different elements. 4 of them are the major elements: oxygen, carbon, hydrogen, and nitrogen. 8 of them are lesser elements. You can see them in the list. And 14 are trace elements. An atom has 2 parts: a nucleus in the center, which contains neutrons, heavy particles with a neutral charge, and protons, also heavy particles, but having a positive charge. The number of protons is equal to the number of electrons. Now, what I'm describing is a model of the atom. No one really knows what an atom looks like, but this model will serve for useful purposes. Electrons are located around the nucleus. They're located in what I like to call energy levels. They're also referred to as orbitals, shells, or orbits. Atoms are mostly empty space. If the nucleus is the size of a softball, the nearest electron will be a mile away. Another model of the atom is to think of the electrons as swarming around the nucleus like bees around a beehive. I know, it seems contradictory. How can they be located in energy levels and yet continue to swarm? Energy levels have a maximum number of electrons. Here's a view of 5 different atoms. The first energy level, being a small one, can hold up to 2 electrons. The second, being a little larger, can hold up to 8. The third can hold 18, and bigger energy levels can hold more than that. There's a catch, however, because the outermost, whatever that may be, can hold up to 8 electrons. These are called the valence electrons. Now, these electrons, they may be gained by an atom, they may be lost, they may even be shared by an atom. The number of electrons is equal to the number of protons. Elements are composed of atoms. The atomic number of an element is equal to the number of electrons or protons. Remember, the number of those are equal. And it's the same in all atoms of an element. The atomic mass, which I often refer to as the atomic weight, and the Dalton is the unit of measurement, the atomic mass is equal to the number of protons and neutrons. Remember, these are the heavy particles. They may be different in atoms of an element. Elements are substances composed of one kind of atom. 92 natural elements exist. The next three screens show a table of the 20 simplest elements and 4 of the larger ones. The elements are arranged in order by atomic number, shown in column 1. The second column lists the names of the elements, and the third its symbol. Those with an asterisk are worth remembering. The remaining columns show the number of protons, the average number of neutrons, and the number of electrons by energy level. Here is a list of the first 10 elements. Notice number 1, hydrogen. It has 1 proton and 1 electron. Helium is number 2. It has 2 protons and 2 electrons. If we continue down the list, we come to carbon, atomic number 6, because it has 6 protons and 6 electrons. Oxygen is a little bit bigger, atomic number 8, with 8 protons and 8 electrons. Notice as we progress down the list, the energy levels fill in order. First of all, the first one fills, then the second one begins to fill, and now we progress to the next 10. The third one has begun to fill, and up to number 18, it fills, and then the fourth begins to add electrons. Here's sodium, for example, atomic number 11. 11 protons, 11 electrons. Chlorine, atomic number 17, because it has 17 protons and 17 electrons. You might wonder, why does sodium have 1 electron in the third energy level? Why not put the electron in the second? Well, because the second energy level can only hold 8. What about potassium? Why 1 electron in the fourth energy level? Because the third, as we said, can hold 18. Why not put it there? Well, of course, the answer is the outermost, whichever that may be, can only hold 8 electrons. And if you put an electron in the third energy level for potassium, it would have 9. Here are 4 other elements for comparison. Number 26, iron, has 26 protons and 26 electrons. Number 79, gold, 79 protons, 79 electrons. Notice the neutrons. Gold has almost 200 heavy particles, whereas iron has roughly 60 heavy particles. So if you have a bar of iron the same size as a bar of gold, gold weighs almost 3 times as much. Notice that as you go up the list of elements, the first energy level will fill before any electrons are in the second, and the second will fill before any are put in the third. Remember, the maximum the first can hold is 2, and the maximum the second can hold is 8. The maximum the third energy level can hold is 18. So why doesn't potassium have 9 electrons in its third energy level, instead of 8 in the third and 1 in the fourth? Because then the third would be the outermost. And remember, the outermost can only hold 8 electrons. The periodic table shows the characteristics of the elements. Each element, for example, carbon at the right, includes the symbol for the element, of course, the name of the element, the atomic number shown above the name, and the atomic mass shown below the name. Isotopes are atoms of the same element having different atomic masses because they have different numbers of neutrons. For example, carbon-12, that's the usual carbon, has 6 protons and 6 neutrons. Carbon-14, on the other hand, still has 6 protons, but it has 8 neutrons. Hydrogen. Normally, hydrogen has 1 proton, but deuterium, a heavy form of hydrogen, also has a neutron. Tritium, another alternate form, has 2 neutrons. Many of these isotopes release radiation. Alpha particles consist of 2 protons and 2 neutrons. Beta particles consist only of electrons, and gamma radiation is a form of electromagnetic radiation. Part C, chemical compounds. Molecules are particles composed of 2 or more atoms or ions. Why do molecules form? They're trying to become stable. Everything there is has a tendency to become stable. Whether it's water in a lake on a mountainside, it flows downhill. Stable means least likely to change. Let's look at 2 pyramids, one resting on its base and the other sitting on its tip. Which pyramid is more stable? The one on the base. What will the unstable one do to become more stable? It will fall over to achieve a stable position. The pyramids in Egypt have lasted in a stable position for 4,000 years. Atoms are stable when the outer energy level is full of electrons. These are the valence electrons. This means 2 electrons in the first energy level, if it's a small atom, because that one is the outermost, 8 electrons in any higher energy level. This is called the octet rule. Note, carbon in this diagram has 4 outer electrons. I just listed them separately instead of together. Are these atoms stable? Can you explain? No, they're not, because none of them has a full outer energy level. How do they become stable? Well, atoms can give electrons, they can take electrons, or they can share electrons. Here is a sodium atom. What can sodium do to become stable? The simplest thing is to give up an electron. When that happens, the second energy level becomes the outermost. Since it contains 8 electrons, that is, it's full, the sodium is stable. What about chlorine? What's the simplest thing chlorine can do to become stable? It can gain an electron. When that happens, the third energy level becomes the outermost. Since it contains 8 electrons, that is, it's full, chlorine has become stable. Sodium and chlorine are now stable because they have 8 electrons in their outer energy level. However, something new has been created. How many protons does sodium have? 11. How many electrons does sodium have? 10. How many protons does chlorine have? 17. How many electrons does chlorine have? 18. Sodium has 1 extra positive charge. Chlorine has 1 extra negative charge. The sodium atom has become a sodium ion. The chlorine atom has become a chloride ion. Now, just because they look alike, don't think they are alike. Sodium and chloride ions are totally different from sodium and chloride atoms. The ions are essential for life. The atoms are poisonous and explosive in the case of sodium and form a deadly gas in the case of chlorine. An ion is an atom or molecule that has gained or lost one or more electrons. An electrolyte is a solution of ions. Ionization is the process of splitting a molecule into ions. Here are examples of ions: calcium, bicarbonate, potassium, and phosphate. Let's look at carbon. What is the simplest thing carbon can do to become stable? Would it give 4 electrons or take 4 electrons? No, this is a dilemma. Instead, it will do neither. It will share electrons, for example, with another carbon atom. This means that part of the time, both electrons are located in the energy level of one atom, and part of the time in the energy level of the other atom. If 3 other carbon atoms also share an electron, the carbon in the center is now stable, because part of the time it contains 8 electrons in its outer energy level. Molecules result when atoms and ions are joined to one another by chemical bonds. Chemical bonds form when atoms give, take, or share electrons. Chemical bonds include ionic bonds. These are weak bonds, at least in aqueous, that is, watery solutions. Covalent bonds, these are strong. Hydrogen bonds, another weak bond. Van der Waals forces, also weak. And hydrophobic bonds, weak. Ionic bonds are attractions of oppositely charged ions. What do positive charges do to one another? Positive charges repel each other. What do 2 negative charges do to one another? They also repel each other. What does a positive and a negative charge do to one another? A positive and a negative charge attract each other. So, like charges repel, unlike charges attract. What will the sodium ion and the chloride ion do to one another? The answer is they attract, and this attraction is an ionic bond. Compounds with ionic bonds are ionic compounds. For example, sodium chloride, another name for table salt. Now, solid sodium chloride forms crystals with very strong bonds. Covalent bonds result when atoms share electrons. It's usually represented as a dash between the atoms, such as the dash between 2 carbons. They form covalent compounds. There are 2 types of covalent compounds: nonpolar and polar. Polar means having opposite sides or ends. A magnet, for example, is polar. The Earth is polar. Political parties are polar. Molecules may be polar. Membranes may be polar. Water molecules are polar due to the arrangement of the oxygen and the hydrogen. The oxygen nuclei attract the cloud of electrons, resulting in a negative end of the molecule. The hydrogen atoms stick out at the opposite end, resulting in the positive end of the molecule. Nonpolar means the opposite sides or ends are not different. Electrons swarm around the nucleus, and opposite charges attract one another. In a nonpolar molecule, the swarm or cloud of electrons is attracted equally to both ends of the molecule, so the charge is the same at both ends. In a polar molecule, the swarm of electrons is attracted to the end of the molecule with the greater positive charge, giving that end an overall negative charge. Hydrogen bonds are attractions between hydrogen and nitrogen, or hydrogen and oxygen. Although weak, these are very important bonds, as you will see as we progress. Water is an example. Here you see some water molecules. Notice the arrangement of the hydrogens relative to the oxygen. The hydrogen of one bonds with a hydrogen bond to the hydrogen of the other. Van der Waals forces are attractions between temporary positive and negative parts of atoms or molecules. You see the swarm of electrons as they rotate around the nuclei leave gaps periodically, exposing temporary positive charges. Hydrophobic bonds are attractions between lipids. Compounds can be classified based on their ability to dissolve in water. Polar covalent compound dissolves in water. Here, for example, is the water molecule with a positive and a negative end, and here are some polar molecules to be dissolved. The positive end of the water repels the positive end of the polar molecule. The negative end of the water repels the negative end of the polar molecule. If you add nonpolar molecules to water, the molecules will not dissolve because the nonpolar molecules have no opposite charged ends, so they remain as a clump. If you add ionic compounds to water, the positive end of the water repels the positive ion, the negative end of the water repels the negative ion, and lo and behold, you end up with a solution of free sodium and chloride ions. With regard to solubility in water, water dissolves hydrophilic substances, including ionic compounds and polar covalent compounds. Water does not dissolve hydrophobic substances such as nonpolar covalent compounds, mainly lipids. With regard to solubility in lipids, lipids dissolve hydrophobic substances, including nonpolar covalent compounds. Lipids do not dissolve hydrophilic substances, such as water, ionic compounds, and polar covalent compounds. In describing water, I'll use these terms. I'll use water soluble instead of hydrophilic and lipid soluble instead of hydrophobic. I do this because they convey the meanings faster than the terms hydrophilic and hydrophobic. Let's look at some other characteristics of water. Because water forms hydrogen bonds between the hydrogen of one water molecule and the oxygen of another, water molecules tend to stick together. This is called cohesion. Water has surface tension. The molecules form a sort of membrane on the surface, such that insects can walk across the surface of a pond. Water ionizes slightly into hydrogen ions and hydroxide ions. Water is sticky, so you lick your fingers when turning a page in a book. Your clothes stick to you in the summer when you sweat. And it's more difficult for a seaplane to take off from a calm lake. The molecular weight is the sum of the atomic weights in a molecule. For example, water, H2O. The atomic weight of hydrogen is 1. There are 2 hydrogens in water, so the total is 2. The atomic weight of oxygen is 16. Water contains 1 oxygen, so the total is 16. Therefore, the molecular weight of water is 18, the 16 plus the 2. What is the molecular weight of glucose, C6H12O6? You'll notice I'll be referring to glucose quite a bit in this course. The atomic weight of carbon is 12. times 6 carbons in glucose gives a total of 72. The atomic weight of hydrogen is 1 times 12 hydrogens gives 12. And the atomic weight of oxygen is 16 times the 6 oxygen gives a total of 96. Therefore, the molecular weight of glucose is 180. A mole is a measure of the number of molecules. It's the weight of a compound in grams equal to its molecular weight. 1 mole of a compound contains something like 6.024 times 10 to the 23rd power molecules. This is called Avogadro's number, an inconceivably large number. Oh, something like 600 billion trillion molecules. A mole of 2 different compounds contains the same number of molecules. Let's consider 2 groups of balls. How many balls are in each group? 4. Which group would weigh more? The yellow balls. Why? Because they're bigger. Assume the yellow balls weigh 4 grams each and the red balls weigh 1 gram each. What is the total weight of the yellow balls? 16 grams. What's the total weight of the red balls? 4 grams. So, if you had 16 grams of yellow balls and 4 grams of red balls, you would have the same number of balls. Here's some examples of mole. Take glucose. The molecular weight of glucose, as we said, is 180. 1 mole of glucose is how many grams? 180 grams. Sodium chloride. The molecular weight is 58.2. 1 mole of sodium chloride is how many grams? 58.2 grams. Since cells are so small, we use 1/1000th of a mole, called a millimole. Let's look at molar solutions. A 1 molar solution is 1 mole of a compound plus enough water to make a 1 liter solution. For example, 1 mole of glucose, 180 grams, plus water to make a 1 liter solution would be a 1 molar glucose solution. How much sodium chloride is needed to make a 1 molar solution of sodium chloride? 58.2 grams. This is the end of the first part of matter. You're now ready to progress to Unit 2, Matter, Parts D to F.